So chapter 4, the big topic is divisibility. With divisibility, we've got factors and we have multiples to differentiate between. And they're often commonly confused. So for example, in one direction, 2 is a factor of 6. And I could say that's because 2 divides 6 with no remainder, right? So that's one way to look at it. 2 goes into 6 3 times. 3 times 2 is 6, and I get no remainder. So you can look at factors as the result of a division, but the other side of the story is you can, in order to do division, we had to know multiplication in the first place. So all the stuff we're doing with divisibility and factors is based on multiplication. So I could also say it's true because 2 times 3 is 6. Because I can find a number to multiply by 2, namely 3, to get 6. So a factor is something used in a multiplication. So factor is a part of a multiplication. So 2 is what I'm focusing on here. 6 happens to be involved. If I focus on 6 instead, 6 is the result of the multiplication. So it's on the other end of the multiplication, so it's called a multiple. So we can say 6 is a multiple of 2, right? It's one of many multiples of 2. So here my focus is on the 6. What's anybody remember the other name for the result of multiplication? The answer. The product, yeah. So a product is a multiple of whatever you started with. So since it was 2 times 3, we could also say 6 is a multiple of 3. So in one direction we have factors, in the other direction we have multiples. Let's switch back to factors for a minute. If we're talking about the factors of a number, like the factors of 6, they're anything that's used in a multiplication that led to 6. So 1 times 6 is 6. 2 times 3 is 6. Are there any other ways to use whole numbers to get 6? Right, those are the only ways. So 6 has 4 factors. And they make a set, so they would be 1, 2, 3, and 6 if I list them in order. Number of factors, you could think about them as the pieces of the number. They're like building blocks. We can build 6 in 2 different ways with multiplication. Sometimes we use the term proper factors. To be proper, you have to be less than the number you're talking about. So the proper factors would be only 1, 2, and 3. So 6 isn't a proper, it's a factor, but it's not a proper factor. Mostly we're going to be spending time on factors, divisors, divisibility in this section, but we got to know something about multiples too, because all factors lead to multiples. Factor means part of a multiplication problem. So as far as multiples go, usually we talk about multiples of a number, so let's keep picking on 6. So what if we look at the multiples of 6? Well, that's using 6 in a multiplication problem. So 1 times 6 is 6. We could say that's the first multiple of 6. 2 times 6 is 12. 3 times 6 is 18. And this list, however, it just keeps going. Because all day long we can make up new multiples by just multiplying something by 6. So if we look at this as a set, and if we're talking about whole numbers, now usually we talk about just counting numbers. Whole numbers, we could do 0 times 6, so 0 is technically a multiple of 6. But mostly we're going to stick with counting numbers. So I'm just going to start with 6, and then 12, and then 18, and then 24, and it just keeps going. So for any number, the set of multiples is infinite. So we get an infinite set of numbers, but there's a pattern to them. They jump by 6 each time, right? And we looked at patterns like that before. So factors versus multiples. So we're going to keep those straight. Back to divisibility. So there's tests for divisibility and there's rules about divisibility. And so we'll play around those. And we have some shorthand notation. So 2 divides 6. And the shorthand for that would be 2, a vertical bar, and then a 6. So that says 2 divides 6. And so you'll see this notation a lot in the homework and in the book. 5 does not divide 6. So that would be 5. We take the vertical bar and we put a slash through it. Does not divide 6. So that's the shorthand for that. Now, we're mostly talking about counting numbers here, so that's 1, 2, 3, 4, and so on. So just some rules of divisibility. So important rules. They're kind of generalizations we can make based on seeing stuff. So earlier I mentioned that 2 divides 6, right? We know that because I can find a number, 3, so I multiply by 2 and I get 6. So that's how I know 2 divides 6. So in general, if we have some number A and it divides some other number B, then there has to be, so there exists, some number n so that A times n equals B. right? And so just think about that. 2 goes into 6. So A goes into B. That means there's got to be something I can multiply A by to get B. And that's going to be a whole number or a counting number. So that's important here. This is a counting number. We're not into fractions or decimals yet. So some other tricks. Suppose that A divides B and A divides C. Then there's a couple of things I know based on that. So if that's true, then A is going to divide B plus C. And if we can talk about integers, also, A can divide B minus C. So we'll test that out with some examples and talk about why it works. We'll look at it a couple of different ways. So we'll just pick some examples. Let's pick a new value for A. Let's say it's going to be 3. So we know 3 divides 6, and we know, say, 3 divides 9. So my rule says 1, then 3 should divide 6 plus 9. Okay. Well, 6 and 9 is 15. Is this a true statement that 3 divides 15? So a way to think about this to kind of justify its truth, we could rewrite these as fractions. So the top one, I could say 6 over 3 equals 2, right? That justifies the fact that 3 divides 6. So I'm looking at it in the fraction form instead of the division form instead of the multiplication form. This one tells me that 9 over 3 is going to be some whole number. In this case, it happens to be 3 also. So then I can rewrite this thing as a division fact. So that would just be 6 plus 9 over 3. I'm saying 3 divides the sum. Isn't that what this says too? 3 goes into that sum. Think about rules for fractions. I can rewrite this as 6 over 3 plus 9 over 3. Think about adding fractions. To add fractions, we just need a common denominator, then we just add the numerators. So when I rewrite it this way, all I'm doing is kind of like unadding what I have here on the left. Does that make sense? And we know 3 divides 6 and 3 divides 9, so that means this sum should be a whole number. Because this is going to be a whole number here, and that's going to be a whole number there. Add 2 whole numbers, you still have a whole number. So in general, as long as A divides one number and another number, it'll divide their sum, and it'll always divide their difference. Now, the difference is interesting because sometimes B is going to be bigger than C, but sometimes not. Is that going to be a big deal? So let's play with the 6 and the 9 some more. So the way I first stated it, I'm saying 3 divides 6 minus 9. 6 minus 9 is what? Negative 3. Does 3 divide negative 3? Yeah, as long as there's a number I can multiply by to get negative 3. So the check here is, yeah, just multiply by negative 1. 3 times negative 1 is negative 3. So we're okay there. If we switch the subtraction, then we just get the opposite of the number we see here. No big deal. We're okay. So that'll work too. In math, we talked about negations of statements, like when we try to reverse the statement back in logic. And the thing I was trying to emphasize there is, if you have a statement that starts off as true, negating it, switching the parts, sometimes it doesn't work so well. The only time it's going to work for sure is if you do it the contrapositive, which means switch them and take the opposite of each. So could I switch, say, these statements right here and still be okay? So what if some number A divides B plus C. Suppose that's the fact I start with. Will that mean that A will divide B and A will divide C? So let's play around. Let's pick a number like, we did 2, we did 3, how about 7? And then let's pick a number we know 7 goes into. Like, 20, I was thinking that same number. Wow, we're on the same wavelength there, 28. Now, it depends on how I break up 28. I could say 28 is 7 and 21, in which case this statement makes sense. But can I break up 28 in a lot of other ways? I could say this is 2 10s and 8 1s, in which case I'd be going 8 and 20, and 7 neither divides 8 nor divides 20. Okay? So the statement I started off with, I can't switch it. I have to start off with the premise that A divides B and A divides C, then I'm guaranteed it divides the sum. But if I start off with a sum, I can't necessarily say it divides the pieces. In fact, it doesn't some of the time. So I can't reverse that statement. But I can twist it in other ways. So check this out. If A divides B and A does not divide C, what do you think is going to be the conclusion about A versus B plus C? Does divide, does not divide, or unknown? So here I have no remainder. Here I have a remainder. I throw them together. Will there be a remainder or not? What's your gut tell you? We'll test it.
I think there would be a remainder.
There's going to be a remainder, yeah. So it's going to turn out it's not going to work. So we'll do a numerical example, and then we'll talk about it more abstractly. So let's pick A to be 7 again. So 7 divides 14. And 7 does not divide 8. Okay. And in particular, we know for sure the remainder on this one is going to be what? 1, right? 8 is 1 7 plus 1 left over. If I put the two of them together, then I have 7 versus 14 plus 8, which is 22. I know 7 goes into 21, so it can't go into 22. What's the remainder here? Yeah, it's that same remainder that this brought into the picture. Because no remainder plus 1 remainder is still going to be 1 remainder there. So that's just an example, but that example helps kind of figure out why it's going to be true in general. And so just for fun, I'm going to use some definitions and just do a little algebra. Oops, wrong way. New page. So, oops, letter. A divides B means, oops, trouble writing again, that there's some number n that I can multiply by A, and I'm going to get B out of it, because there's no remainder. If A does not divide C, that means there's going to be a remainder. So that's going to mean that if I take A times some whole number, let's call it Q, I'm going to have to add on some remainder so I can get C, because it's not going to work perfectly. So when I try to take B and C and put them together and see what A can do with this, my claim is that it does not divide B plus C. I just look at what B is equal to and what C is equal to according to definition of divisibility there. And I can rewrite this and say, I'm trying to take A, oops, highlighter. I'm trying to take A into B, which is really A times some number. And I'm trying to take it into C, which is A times some possibly other number plus a remainder. Now, keep in mind the remainder, if A is 7, what are the possible remainders I can have? If A is 7.
1 through 6.
Yeah, 1 through 6. Now, it can't be 0, right, because we said it doesn't divide. So you're right, it's going to be 1 through 6. So R is going to be some counting number that's less than whatever A is. So now when I look at this group of things right there, I can factor that A out, and I have A times N plus Q. And then R is just hanging out. So if N is a counting number and Q is a counting number, do I still get a counting number when I add them up? Yeah. But I still also am stuck with that remainder. It just carries along. So anytime you add on a number that's going to have a remainder, you're stuck with that same remainder. So if A was 7, R is like 1, 2, 3, 4, 5, or 6. And I can never get rid of it. All right, so there's a few more rules, but they're not as exciting as the stuff we're about to do. Next, we're going to talk about divisibility tests. Divisibility tests. So what a test is trying to see if it divides without actually dividing. So we're checking divisibility without actually doing division. Okay. So, for example, is 1,392 1,392. Is that divisible by 2?
Yes.
You didn't divide, did you? Okay, so we have a quick test on that one. So how can I tell if something is divisible by 2? It ends in an even number, okay? Ends in an even number. One question about that. What does it mean to be even?
There's there's no odd man out, I guess, in that number.
There's no odd man out. Okay, so how can I tell if there's no odd man out?
You like put 2 in it, multiply by 2 to get it.
Okay, so being even means divisible by 2, but I'm trying to check if the number is divisible by 2, right? So we just did a loop there. Okay, so we got to do a little better than that, and it's not too bad, because you guys just looked. Give me some other examples of even numbers to end in. What else could I have ended in?
0.
0.
4, 6, 8.
Yeah. So that's the more technical way to say it, because we're trying to see if something's divisible by 2. So we say, okay, it's got to be even. Well, how do you know if it's even? Well, it's divisible by 2. Wait a minute. That's what I'm trying to figure out. So it's even or divisible by 2 if the ones digit is in this set, 0, 2, 4, 6, or 8. Those are our even digits. Why are they even? Because 2 goes into them without a remainder, right? So once we know that 2 divides these without a remainder, anything that has that as the 1 digit or that ends in that, we know it's got to be even too. Okay. So that's our test for 2. Does anybody know a test for 3?
Isn't it like if you add each digit in the number?
Yeah, if you add each digit in the number. Yeah, this is way cool. Divisibility by 3. If the sum of the digits is a multiple of 3. then we have divisibility by 3. So for example, take that, what do they just have? 1, 3, 9, 2, is that what it was?
Yeah.
Yeah. So 1 plus 3 plus 9 plus 2, 1 and 3 is 4, and 9 is 13, and 2 is 15. Since 3 divides 15, 3 must divide 1,392. So we can double check that by actually doing the division, taking 3 into 1,392. So 3 goes into 13 4 times, remainder 1. 3 goes into 19 6 times, 6 times 3 is 18, remainder 1. And 3 goes into 12 4 times. Yeah, 3 times 4, 64.
That works every time.
Works every
Oh my
time.
gosh, I've never heard of that before.
It's nuts, isn't it?
Yeah.
Yeah. Okay. Do you want to know why it works? Yes? Okay. So we're just going to let's just do a check on 3-digit numbers. So if I have a 3-digit number called ABC, that means I have A hundreds, and I have B tens, and I have C ones. Right? Okay. Now, 100 can be rewritten as 99 plus 1. And 10 can be rewritten. Oh, did I mess up my colors? It did. You starting to see where I'm going with this?
Yeah.
As 9 plus 1. And C, well, C is just 1 C there. So then I distribute my A through here and my B through there. So then I get 99A plus 1A, and I get 9 B's plus 1B plus C. If I reshuffle those, I have 99A plus 9B, and then I have plus A plus B plus C. So here's the sum of the digits. Now, one of the rules I gave earlier is that if a number divides one thing, and another thing, and another thing, then it will definitely divide the sum of those things. Does 3 go into 99 times A? Yeah, because it goes into 99. I don't really care what A is. It goes into 99. So it's going to go into 99 times A. Does 3 go into 9B? Yeah, because it goes into 9. So as long as 3 goes into A plus B plus C, we're good. And that's the reason behind it. Now, based on that, can you see that we're going to have another trick for divisibility in a minute? What other number might this help us out with?
It'll help you with other multiples of 3, wouldn't it?
Well, multiples of 3. So we're testing 3. Is there any other number that this might help us test besides 3?
I was thinking.
Yeah, because check it out. If 9's going to go into this and 9's going to go into that, so as long as 9 goes into the sum of the digits, 9 will go into it too. So the same trick works for 3 and 9. Now that's only a 3-digit number, you might say. Well, it turns out any multiple of 10 can be written as a bunch of 9s plus 1. Okay? Like think of 1,000, that's 999 plus 1. 10,000, 9,999 plus 1. A million, 999,999 plus 1 is always going to work. It's kind of cute. Can't remember, when did I learn that trick? I think I didn't learn it until high school. You know, it just kind of depends. Did you have the right teacher on the right day and you remember hearing it? But it's a pretty cool trick. So you've heard this one before, right? About the 3s. Tiffany, Caleb, or Nikki, have you heard that before? That's new. Okay. That's pretty neat. All right, so let's see. We got a rule for 2. We got a rule for 3. Can you think of any other numbers that you already know rules for?
5s.
5s, yeah. What else?
4 has one, I don't remember what it is.
4 does have one. Yeah, we'll do that one in a minute. So 5, rule there would be ends in 0 or 5. 10 ends in 0. Another cool one, we can make a rule for 6 because 6 is 2 times 3. So we just test for 2 and we do the test for 3. If it passes both tests, it's got to be divisible by 6 also. So that would mean we want it to be even. Even, again, means ends in a 0, 2, 4, 6, or 8. Oops, curly bracket. And we would want the sum of the digits to be a multiple of 3. So for example, 192. It's even, check. And then 1 plus 9 plus 2 is 12, and 3 goes into 12. So you might say, well, what if the sum of the digits adds up to a 6? Is that going to be good enough? The answer is, if you look back here, 6 doesn't go into 99, and it doesn't go into 9, right? So it's more than that. And then consider something like 492 as another example. It's even, right? And if I look at the sum of the digits, that's 4 and 9 and 2. 4 and 9 is 13, 14, that adds up to 15. 3 goes into 15. So this is even and it meets the test for 3. So my claim is 6 goes into it, but 15 is definitely not a multiple of 6. Okay. So the test has got to be, it's got to meet the 2 test and it's got to meet the 3 test. If it meets both tests, because 2 times 3 is 6, then we're good. All right, let's see. 4, we're going to talk about 4. 4, the number has to end in a 2-digit multiple of 4. So like 1,509,316. 4 will go into that because 4 goes into 16. Okay. The question is why will that work? And we can focus on the hundreds digit to kind of figure it out there. So if I just focus on 316 for a minute, 316 is 3 hundreds plus 16. Now, I know 4 goes into 16. Does 4 go into 3 times 100? And the reason it does is because 4 goes into 100. Now, if 4 goes into 100, 4 is going to go into 10 times 100, which is 1,000. Or 10 times 1,000, which is 10,000. Or 10 times that, which is 100,000, and so on. So 4 is going to go into 9,000, 4 is going to go into 500,000, and 4 is going to go into 1,000,000 because all of those are multiples of 100, and I know 4 goes into that. So it goes back to, oh, there was another rule I forgot to mention. I'll come back to that. But again, because 4 will go into all of the other bases for each of those places, the place values, all we need to ensure is that it goes into the first, the number made by the first pair of digits. So we can just look at that there. So the rule I forgot to mention that's pretty important way back here. Let's see. Yeah, I'll put it after this slide here. So we have the, oh, and one more, and one more. Here we go. Yeah, so this rule is an important one. Next to it, I'm going to add another important rule. If A divides B, then A will divide any multiple of B. Because if there's no remainder when we do the B, there's going to be continued to be no remainder with the multiples of that. So I think these three rules are the most important ones in terms of divisibility. We can do an amazing amount of math with them based on that. So the nice thing about divisibility rules is we want a rule that's slightly easier than division. Otherwise, why have the rule? So again, rules we've collected so far. Or tests, excuse me, divisibility tests. We have a test for 2, we have a test for 3, we have a test for 4, we have a test for 5, we just made a test for 6. There's no easy test for 7. There's a harder test. Maybe I'll show that next class, but maybe not. What else do we have? We have a rule for 9, 10, and ooh, I think that's as far as we've gone, haven't we? Yeah, all right. So it turns out there are some other rules that are kind of cool. A rule for 8. And it's similar to the rule for 2 and the rule for 4. And it kind of goes by this pattern here. 2, we're going to call that 2 to the first power. And 4 is 2 to the second power. If I put 8 in this list for a test, 8's going to be 2 to the third power. So with 2, I only had to look at the ending digit. For 4, I had to look at the ending pair of digits. Guess what I'm going to have to look at for 8? Yeah, I'm going to have to look at what the number that's made by the last 3 digits. So hundreds, tens, and the ones. So if the number, there we go. Made by the last 3 digits is a multiple of 8, then we're good. So for example, let's look at 136, I'm pretty sure 8 goes into that. So suppose we have 5,136. So my claim is 8 goes into 136. How many times? 17 times, I think. Double check. 17 times 8. 8 times 7 is what? 56. 6, 8, and 5 is 13. So yeah, so there's 136. So then what I do is I break this down. This is 5,000 plus 136. Now I already know it goes into 136. 5,000 I'm going to look at as 5 times 1,000 plus 136. Oops. And 1,000 is 10 cubed. Now 10 is really 2 times 5. So that means 10 cubed is really 2 cubed times 5 cubed. And then I have this other 5 out front. And 2 cubed is really what? 8. Yeah. So if 8 goes into 1,000, it's going to go into 10,000, then 100,000, a million, and so on. So the catch here is as long as those first 3 digits form a multiple of 8, we're good. 8's going to go into it from there. Now, problem, how many of us have the 3-digit multiples of 8 memorized? I certainly don't, right? So this is kind of a marginal test. It's cute because it forms a pattern with 2, 4, and then 8. And we can do a similar thing with 16. But the problem with 16 is the first 4 digits would have to form a multiple of 16. And I don't know a lot of 4-digit multiples of 16 off the top of my head. So there's a lot of tests we can make that are similar, but they aren't necessarily useful because they're harder than division. All right, 11. 11 has an amazing one. So let's see. I got to cheat here and make a multiple of 11 so I can test it. We'll do in suspense for a minute. Okay, so let's take 597,531. 597,531. Get that right? 597,531, yeah. So here's the trick. What you do is you alternately add and subtract the digits. Like with 3, we add the digits. So what I do here is I start with 5, and then I subtract 9. And I add 7 and subtract 5. And I add 3 and subtract 1. Okay, so what happens when I do that? 5 minus 9 is -4. 7 minus 5 is 2. 3 minus 1 is 2. -4 plus 2 plus 2, that adds up to 0. What I'm hoping is whatever I get here is a multiple of 11. Is 0 a multiple of 11? Yeah, because 0 times 11 is 11. Yeah. So it turns out 11 must go into that number. Okay. So we just alternately add and subtract the numbers. The digits, excuse me. And what we're hoping for is a multiple of 11. So if I take 11 times 5, 4, 3, 2, 1, 54,321, this is the number I get. That's how I came up with it there. So let's just randomly make up a number and check it. So, Caleb, give me 3 digits.
7, 2, 9.
All right, Tiffany, 3 more digits.
6, 8, 4.
It's hard to go with random digits, isn't it? It's hard to be random. Okay, so does 11 go into this is the question. So we'll just do 7 minus 2 plus 9 minus 6 plus 8 minus 4. Let's see, 7 minus 2 is 5. 9 minus 6 is 3. 8 minus 4 is 4. 5, 6, 7, 8, 9, 10, 11, 12. And that's up to 12. So therefore, 11 will not go into this. So let's whip out a calculator and check. Is my calculator working today? I can fix that soon. So 729,684. So 729,684 divided by 11. I should get a decimal out of it. Okay, so it doesn't work. Now, it was close, though, right? 12 is almost a multiple of 11. So could we tweak one of those digits? Yeah, we could drop any one of, well, not any one of them. Let's say we could drop the 4 to a 3. So if I take 729,683, then when I do the sum of the digits, 7 minus 2, 9, minus 6, plus 8 minus 3. Let's see, no. I want to bump that up to a 5. That's what I want to do. because I want to take one more away from this to get 11. So that's going to give me 5 plus 3 plus 3, 5, and 3 and 3. That's definitely 11. So we should see that this is some multiple of 11. We whip out a calculator. 729,685. So it's 66,335 is the multiple that we found. The trick for why it works is related to the trick for 9 and 3. So check this out. Let's take 10,000, 1,000, and 100, and 10, and then we have the ones here. So 10 is 11 minus 1. Okay. 100 is 99 plus 1. 1,000 is what? I think it's 1,001 minus 1. And somebody with a calculator, how many times does 11 go into 1,001?
91.
What is it?
91.
91 times, exactly 91 times, right, no remainder. So it turns out that you can keep rewriting. This one right here is going to be 9,999 plus 1. So 11, it turns out, it has multiples that alternate with powers of 10. So with any power of 10, 11 is either going to be have a multiple that's 1 less than that or 1 more than that forever. So that when you break that down, if you had some number like A 10,000s, B thousands, C hundreds, D tens, and E ones, each place value like 10,000, we're going to rewrite as 9,999. So A is going to be, I'll have A 9,999 plus A. And then I'll have plus B times 1,001 minus B. And then I'll have C times 99 plus C. And then I'll have, I'll have D times 11 minus D. And then last I'll have plus C. $11 I know goes into 9,999. I know it goes into 1,001. I know it goes into 99, and I know it goes into 11. So then I just take the digits, A minus B plus C minus D plus C, or E, that was supposed to be, sorry. And it's going to work. Now the trick for the alternating part is this version of it says the ones digit always has to be added, which means the 10 digits should always be subtracted. If you change the order of the subtraction, you're just going to get the opposite of a multiple of 11. So instead of ending up with 11, you might get negative 11 because you have the subtraction in the wrong order. But that's no big deal. It's still a multiple. 11 is a multiple of 11, and so is negative 11. So it's a little harder trick than about the 9 and the 3, but it's the same idea. Just because 11 happens to have a lot of great multiples right next to alternating in order before and after multiples are powers of 10. Okay, I think that's enough divisibility stuff for now. Do any of those activities directly relate to divisibility? I think the activities start up with section 2. Square experiment. Oh, that's a good one. Yeah, let's do a square experiment together. Let me get that printout for you. And let me make a note of the activities I'm sure we're going to do. So we're going to do, this is chapter 4, activity 2, activity 3. That one will play Monday. Hopefully everyone will be here for that, because it's a good one to play with a partner. It's kind of boring without a partner. Activity 4 we'll do for sure. I'd like to do the square tiles, but we'll see. That's a maybe. So let's just say 2, 3, and 4 for now. So I'll add that to Canvas to remind us. And those will be due till the end of next week. Well, let's start this one here. So let me copy this into, let's see, my workbook. Play a graph paper with me. Bless you.
Bless you. Thank you.
So a couple things we're going to need to do this. We're going to need that chart because we're going to fill it out, and then we're going to need some graph paper. This one should work. This is on my grid.
Back here.
Yeah, right there is fine. Thanks. How about in the medium grid, maybe? That'll work. So let's go over their example for 4 by 8, and we'll try it for 6 by 9, and then I'll set you guys free to take a look at it. So start off by drawing a 4 by 8 grid on your graph paper. So then what we want to do is we want to check, can we cover the rectangle we made with 1 by 1 squares, 2 by 2 squares, 3 by 3 squares, 4 by 4 squares, and so on, without leaving any gaps. So 1 by 1 is always a pretty much given. We have that on the paper. So we're always going to get the 1 by 1 right away. As far as 2 by 2 goes, we want to double check that that's going to work. So if I come making 2 by 2 squares all over it, am I going to be able to cover this whole region? And turns out 2 by 2 works. So this is kind of an exploratory activity. So we try it for a 3 by 3. And right away I can see as soon as I draw the first 3 by 3 in there, I have a gap. Vertically, so no point in continuing. So 3 by 3 failed. So then I try 4 by 4. So here's my first 4 by 4. And here's another 4 by 4. 4 by 4 worked. And I can't go any bigger than that because I've met my height here. So I'm done. So I found a 1 by 1 square will tile this floor, a 2 by 2 square will tile this floor, and a 4 by 4 square will tile the floor. Okay, so let's write that down in our grid, or they already wrote it down in the grid. So back to, where'd my grid go? Oh, there it is.
Which activity is this?
This is activity number 2. Am I on the wrong one? Uh-oh. Oh crap, I'm on number 5. That's embarrassing. Let's try again. Ah, here we go. Sorry about that. We'll get to that one later, maybe. Since we started it, we might as well try next week. All right, new page. Always nice when I can make myself blush in class. All right. So let me copy this grid. Thank you for asking what the hell I was doing.
I was thinking, I don't know.
Feel free to interrupt me. Say, Parker, what's going on here? You are not in the same universe we are right now. Okay. So this one's a little bit different. In this case, we want to use the graph paper to build rectangles that have this number of squares in them. Okay. So for example, let me get the graph paper out again. If I pick on 4, I can make a 1 by 4 rectangle, or I could make a 4 by 1 rectangle, but I could also make a 2 by 2 rectangle. So I get 3 different rectangles I can make for 4. Which other ones didn't they do here? Did they do 6? They did 6. 5, what do we got? 5 could be a 1 by 5, or it could be a 5 by 1. For 4, I had 1 by 4, 2 by 2, if I put them in order, and 4 by 1. 2 would just be 1 by 2 or a 2 by 1. 1 would be a 1 by 1. And then let's keep going. 7, 1 by 7, or 7 by 1. What about 8? Let's see. 1 by 8. Oops. Or 2 by 4. A 4 by 2. Or an 8 by 1. So given that could be a long rectangle or a tall rectangle. 9, 1 by 9. Now for us, it's pretty easy to kind of visualize this, but kids are going to definitely want to draw it out on paper. 9 by 1. 10. 1 by 10. 2 by 5. I can't do a 3 by or a 4 by, but I can do a 5 by 2. 6 won't work, 7 won't work, 8 won't work, 9 won't work, but 10 by 1. What would be an alternative to using graph paper for this? For kids. Yeah, just give them a bunch of blocks and say, hey, grab 10 blocks. How many different rectangles can you make? And get them together in groups and see what they come up with. 1 by 11, 11 by 1. 12 is a lot more exciting. 1 by 12, 2 by 6, 3 by 4, and then reverse each of those. 4 by 3, 6 by 12, 6 by 2, excuse me, and a 12 by 1. And then what I want to do is I want to count how many different ways I made these rectangles for each number. So there was only one way to do 1. There were 2 ways to do 2, 3 ways to do 4, 2 ways to do 5, 2 ways to do 7, 4 ways to do 8, 3 ways for 9, 4 ways for 10, 2 ways for 11, 6 ways for 12. So there's a couple of things that these finished results are going to tell us. So one thing it tells me is the number of factors a number has. And it turns out numbers that have exactly 2 different factors are very special in math. So on the left side here, what's special about 2, 3, 5, oops, wrong one. Do that. 2, 3, 5, 7, and 11. Numbers that ended up with exactly 2 different rectangles. Anybody remember? They are prime numbers, yeah. So if they have exactly 2 factors, they're called prime numbers. 1 isn't considered a prime because it only has a single factor. It doesn't have 2 distinct factors. Okay, so 1 is not a prime number. Now, other than that, if numbers have more than 2, so all the numbers that are unhighlighted, they're called composite numbers. So this one, and 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 this one, those are composite. So as far as multiplication goes, it means they have other numbers as divisors. Prime numbers, 1 times 2 is kind of lame. 1 times 11, that's kind of a lame set of factors. Right? It's pretty basic because 1 as a multiple doesn't do anything. So that's what makes them special. But there's another interesting thing that pops out. Sometimes we have an even number of factors, and sometimes there's an odd number of factors. So I'm going to highlight the numbers that have an even number of factors. Or sorry, an odd number of factors. Let's see. 1 has an odd number of factors. 4 has an odd number of factors. Who else? 9 has an odd number of factors. And it turns out 1, 4, and 9 are part of another special group in math. Anybody guess?
Squares?
They are perfect squares, yeah. If it's a perfect square, then what's going to happen is you're going to get this middle rectangle that you can't flip it. A 3 by 3, if you flip it, it's still a 3 by 3. It hasn't changed because it's a perfect square. But otherwise, with like 8 and 10, I have 2 times 5 in the middle, which is also 5 times 2. I can flip it. 2 times 4 versus 4 times 2. But if it's a perfect square, it's going to have this perfect square array in the middle of the possible arrays that we can make. So if you turn the page in this activity, we want to list those numbers that had only 1 array, 2 arrays, more than 2 arrays, and odd number of arrays in these columns here. So let me add a new space and stick that in. So let's see, what number had only 1 array? 1 was the only one. Numbers that had 2 arrays, those were the 2, 3, 5, 7, 11. Numbers that had more than 2 arrays were 4, 6, 8, 10, oh, I forgot 9, 12, And the odd arrays, 1, 4, and 9. So what's the name of the things that are in column B here? Yeah, those are our prime numbers. What's the name of the stuff in column C? Those are composites. Yeah. And the names of the things in column D with 3 arrays, those are perfect squares, right on. Yeah. And what we're going to spend a huge topic in the rest of chapter 4 is going to be the idea of prime numbers and the things we can do with them and the things they tell us about math. And that's what we're going to spend the rest of our time with. So let's answer a couple more questions, then we'll call it quits for today. 24 can be made up into rectangular ways in a bunch of different ways. Now, just to look at this in a slightly different way, 24. When we're playing around with numbers and divisors or factors, there's a couple of different things we do. One is listing factors. And another procedure we do sometimes with a number like 24 is we make a factor tree. So I just want to differentiate between those two techniques. With listing factors, what I do is I look for pairs of numbers that multiply to give me 24. So listing factors as pairs. The most basic one is 1 times 24. Then I check 2. Is 2 going to 24? Yeah, 2 goes in there 12 times. Then I check 3. Is 3 going to 24?
Yes.
Yeah, 8 times, right? Is 4 going to 24?
Yes.
6 times. Does 5 go into 24? Nope. And then I get to 6, which I've already gotten. Okay. So I could keep repeating this like the arrays we were doing, and I'll get just repetitions of these. 6 times 4, 7 doesn't work. 8 times 3, 9 doesn't work. 10 doesn't work. 11 doesn't work. I get 12 times 2. And then there's a whole bunch of numbers right from 12 to 24 that don't work. And then finally, I see 24 times 1. When I list all of these rectangles, there's 1, 2, 3, 4, 5, 6, 7, 8 rectangles. They represent the 8 different factors there. The factors are 1, 2, 3, 4, 6, 8, 12, and 24. So that's one efficient way to come up with a list of all factors. Now that's different from a factor tree. A factor tree is where I say, well, 2 goes into 24 12 times. I note that 2 is prime, nothing goes into it besides 1, so I leave it alone. Then I break down 12. How would I break down 12? Or how could I? There's lots of ways. I could go 2 times 6, right? And nothing much I can do with 2. 1 times 2 is kind of boring, so we ignore 1. Then I look at 6 is 2 times 3. What a factor tree gives me is what's called the prime factorization. So 24 is equal to 2 times 2 times 2 times 3. I just look at the answers at the end of the branch. Now somebody else might do the factor tree for 12 different. Somebody else might say, well, I remember 24 as being 3 times 8. And then look at 3, and no, there's not much I can do with 3, but 8 I know is 2 times 4, and 4 is 2 times 2. And so somebody might argue with you, no, the prime factorization of 24 is 3 times 2 times 2 times 2. Right? Is there much of a difference between that prime factorization and this one? Just a different order, and we can multiply in any order we want. Sometimes it's easier to write exponential notation, so I could say this is 2 to the third power times 3. Or even maybe 2 to the third times 3 to the first. Sometimes you'll see that first power written in there. We have a couple of ways to do that. So factor tree, that gives me the prime factorization. That's useful sometimes. List of all factors, that's when we look for pairs of numbers that give me the number in question. Okay, so 2 different techniques, 2 different lists of numbers. They both are important and they have different uses that we'll play with over the next couple of sections. All right, let's see what else, anything else we should take a look at here. So we have factors and primes, the names of those columns. All right, and I think I haven't answered these directly, but I've addressed each of these questions down here. All right, so we'll stop here. Next week we have 2 days. On Monday, we'll just finish stuff up. We'll get to section 2. Actually, we've already started section 2 because we're talking about prime numbers. Section 2 is about prime numbers. It looks pretty unlikely we'll get to section 3. We'll talk about it a little bit, but I don't think we'll have official homework for that. And then a week from today, we'll start getting ready for the final. And Monday, I'll have a take-home final for you. I already practiced a sample. I posted a sample final. I don't know if everyone's looked at that yet, and answers for it. So take a look at that sometime soon. It's under the other resources page. There's a sample final and then some answers there. All right, so have a great, safe Thanksgiving, and we'll do more fun math next week.